All right, everyone, good morning or afternoon, depending where you're joining us from. I want to welcome you to Introduction of Deep Learning, brought to you by Eduonix. So the new stuff that we're doing today, we're going to be doing some movie recommendations with Keras. For those of you that were with us last week, I know I brought up doing some image classification with the fashion data set. I'm going to reference it a bit today. However, I figured, image classification is only one of the things that Keras and TensorFlow are really cool for. So I figured we'd do something a little bit different this weekend as well. So first question here is, what is a recommender system? Okay, so I have a recommendation system can offer suggestions of relevant items to users. Personalization system that offer recommendations to purchasers. Those are two great definitions here of what we're thinking about when we think about a recommender system. So if we think about what that is, essentially it's something that is going to recommend you what you may like. So depending what social media you use, if you use Amazon Shopping, eBay, what's the other big one? Rakuten is another huge one where they use big time recommender systems. And the key idea there being is that it's using similarity preferences. So on things that you've posted, so it's looking for similar items. So some popular users, Netflix is a big one, Amazon, YouTube, and basically anything that tracks your data and makes money from advertisements. So as we know, a lot of apps that exist today are free to begin using. So what they really rely on is those back-end kind of recommender systems so that they can gain points off advertising. The best way to get good advertising payments is to verify that, hey, like if you're advertising on our site or within our application, you're going to see return on investment. So that ROI piece to it of, how long someone's looking at an advertisement, how long a video they're watching, capturing that screen time, as well as returns. So how often are the clicks turning into purchases? So a formalized or kind of informal goal, I guess you could say, of recommender system is to predict what a given user may wish to purchase either for the first time or again in the near future. So the key idea of it's going to happen soon. So it's not you're not going to show someone a house if they're not, if they looked at a house one time, that's probably not going to show up in the recommender system. However, if that's something that they're consistently viewing, then perhaps, their Facebook page is dropping more and more advertisements of houses for sale in the nearby area. So today we're going to work with is sentiment analysis. So sentiment analysis is basically making sense, getting the feeling or the mood of text. So this falls under the branch of natural language processing. So that's going to kind of be our theme for the weekend here when we work through these, is looking at how sentiment analysis can be implemented using TensorFlow and Keras. All right, so getting the data we'll need. This is something just I thought would be nice to have as a bookmark or a reference for all of you of the different Keras kind of training data sets that are available. Oftentimes, one of the most challenging parts of building models on our own is finding data that can be used for it. So again, the idea of a quote unquote toy data set basically mean it already exists and there's been a lot of work done on it. However, they're great for learning on. They're great for developing that repository of code. That's where we're getting all these lessons from, is just coding I did before on my own to kind of build up my skills in this. So when we have all this idea, here's some other ones you could look at is the TensorFlow data sets. They're also available. However, Keras is pretty handy. You'll find a lot of resources on them. So this is one we worked with so far. The MNIST, so the MNIST, that was the digits classification. If you're looking for something with the fashion one, that one also is down here. And what's nice is you'll notice these all have that call function of load data. So meaning there's no real downloads needed. You don't have to, find this data, download it, then load it as a CSV. It's all just kind of there and ready to go for us, which is a nice feature. So some other things we're looking at here is this is the one we're working with today. So the IMDb movie review sentiment classification data set. So if we click on it, it'll tell us some of the stuff to load on. So what I want to give everyone a chance to do here real quick is take about 2 minutes and just glance through this page just to learn a little bit about the data set. I realize that's something that oftentimes we don't build in time to do, is to really kind of preview the data set that we'll be working with. All right, so what this does is gives you different options within the load function. We won't be using the full formalized version today. We're not going to kind of skip through some of the specific cuts here that you can do. However, hopefully, at least if you've read this part here, you kind of get the idea of what the data set is. So talking through this a little more, how we're going to get this data. Get here, there's 50,000 movie reviews and we're pulling in the top words. So we're only looking at certain top words here. So it didn't get all 25,000. However, we'll kind of chunk that down a bit just to make it a bit more manageable on RAM and the different processing power we have. So key idea here is the sentiment being either a positive or a negative review. So the idea of this recommender system here is that we're identifying which movies or which categories have those positive versus negative reviews and how well we can predict that. So from looking at the text, the key idea here is that we're given a lump of text, and then all of these training examples have that positive or negative side attached to it. So the goal here of building a system like this would be to say, okay, just from reading a review of the movie, can we decide if it's a positive or a negative sentiment? So positive or negative review. How this would build into a recommender system would be that if you were looking at someone's reviews of movies on a website, you could recommend or predict ones they'd like such that they're similar movies. So here's the idea of it being encoded as a sequence of word indexes in the form of integers. So similar to how we've seen on there, meaning it's saying how many times a word occurs. And then their frequency. So the index, the words that are most frequent are shown first. Then where this comes from was created by researchers at Stanford University and published back in 2011 in a report. We'll see today if we could actually beat their accuracy. I think their accuracy was in like the low 80s back in 2011. So we'll see if we can build a model leveraging Keras to see if we can beat this. So if you want to go ahead and open up a Jupyter notebook, we can get started with coding. Oh, and I forgot one. Let's go ahead and do. We'll get that data set in our imports as well. So if everyone wants to take a minute, go ahead and run that as well. We already installed both Keras and TensorFlow last week, so I'm under the assumption you have those installed. All right, so what we brought in here, we have NumPy, that's one we've seen so far. We've matplotlib, and matplotlib.pyplot is PLT, so that's gonna be sort of some visualization, some graphing. If we go down, we got inline, just meaning that we kind of have that nice vertical lineup so that it looks a little more clean. TensorFlow is TF, so again, the common import here. If you're looking at, sample code online, most people bring in TensorFlow as TF. So again, the kind of that shorthand, like pandas is PD, NumPy is NP. Keras.utilities, and we're putting two categorical. So we'll be using that later on. Then we have models, and then we have layers. And then lastly, this is the kind of shorthand way to bring in that data set. So that'll work with any of those different ones we had on there. All right, so I'm gonna go ahead here and write out a nice way of getting our training and testing data together. So again, give me a second, let me type and then we'll discuss. Oh, put this backwards. What is it not like that I'm doing? Let me see here. What is it not liking? Let's see. Format that. Okay, there we go. I had too many spaces. All right. I think it was just not liking the way I had that typed over here. So we're good there. So what this is doing is we're just kind of splitting in our training data and targets. So this is just another way of loading this data set. So with a lot of these pre-built data sets, there is some nifty loading functions. Now, something to consider is if you're working with, kind of what I would call real world or live data, you're not always going to have it, preloadable like this. So one of the other often, I guess you could say, less considered things of when you're looking at real world data and building it into something you're going to work on with this type of stuff. So Keras or TensorFlow is the idea that there's a lot of preliminary stages to it. So in some of our earlier work together, we talked about data exploration, we talked about some basic data cleaning and data formatting, reshaping, transforming data. Those are those kind of essential skills that you're going to need a lot of to get to this point. So something I would suggest is the reason why I keep all these reference files handy is because if I'm working with real data and I want to build it into a model like this, what's going to take a lot of time is getting that raw data input usable. So a project I'm recently working on through the American Board of Surgery is dealing with intaking data and then making predictions from it for surgeries. So the way we have to do that is there's a lot of cleaning up front. So that's the preliminary stage we're now is working on the idea of cleaning things to make it predictable, to make it usable so that I could even import it into something like this and do some more advanced modeling with it. So that's something to consider too. These training data sets are great to have handy. As I'm working on building in and transforming data, I'm often looking for the most similar Keras data set and like, okay, like how is this structured? Because once I can get the data at structuring level, I already have the code that does the training, and I could mess around with the model and try and optimize it. But the key idea is that you have to get the data to a usable format. So even if you're, just kind of getting the idea down of like what the model looks like, that's awesome. But you want to keep those resources like that Keras link I sent handy, just so you can go back and look at those data sets and kind of see like, okay, like if I want to do sentiment analysis, I need to make my data look something like this. All right, let's go ahead and get our next line here. So go ahead and say data. What we're gonna do is use NP's concatenate function. So this is kind of similar to the one you've likely seen it with pandas if you've used that at all. We're gonna use numpys today just to put some data together. I forgot the testing. There we go. So we're just putting the data together. So we read it in its two files, and then now we're combining it. So now we're just kind of grouping our data and our targets together so that we have them in these larger data frames just to do a little bit of exploration with them. All right, so let's go ahead and do a little exploring with this data. So let's look at the categories we have. So this is a nice way of using kind of print statements throughout just to see what it is we're getting, what it is we're looking at. And hopefully you're seeing a little more of the power of the NumPy package today. Plural. There we go. So what we're seeing here is those targets we talked about. So the sentiment classification of 0 and 1, 1 and 0. So this falls into binary data. So that's one of the best things to do is if you're trying to do this and in real life, as I would say, is start with binarizing your data. So one of the models, one of the first times that I worked on something in this field was doing personality classification. Due to non-disclosure agreements, I can only be so specific with these examples. So I apologize for any vagueness in there, but in the line of work I do, everything's under non-disclosure agreements. So I can only legally say so many like nifty little things with it. But it was working with personality profiles from a online location. So one of the things I found in here was that if you ever looked at different personality profiles, there's a lot of them. There's like 16. So when you're trying to model something to 16 categories, like you need massive, massive amounts of data, as well as some key indicators with that. So what I found when I was modeling is that when I tried to do like all 16 of these at once, it was really just low accuracy. And like I had a good size set of training data and like it was nicely cleaned. Like I cleaned it myself, built it out. It honestly looked really similar to this. The only difference was my targets were like, 0 through 15 instead of 0 and 1. When you have that level of kind of challenge within a data set, what I found beneficial was to boil it down into tiers. So the way I built that model was I actually had it predict just one thing first. So instead of shooting to 16 different categories, it shot to just, A or B. And then from the A category, it ran another model and said, okay, does it go to, category C or D? From the other category, it's split again. So almost making like a tree diagram, I found was easier to model on in that way, because it kind of simplified the modeling process so that I could make it better at each stage. So anytime when you're modeling, the idea of binary classification is nice. Now, again, it's always not the most practical thing, because in a perfect world, if we were doing sentiment analysis, we wouldn't just want to do, positive or negative. We'd want to have some different almost Likert scores in there, like strongly like, kind of like, not really like, or dislike, strongly dislike. But again, in the idea of building modeling, Occam's razor always comes into play in data science. Like the simplest is the best. So if you can think of, success or failure, positive or negative type categories, it makes the models, I guess you could say, it gives them more data to train on, and it kind of allows you to, really focus on each layer of that model a bit more. All right, so let's see how many words we have in here. One, two, three, four. Okay. Let's go count the parentheses at the end. So what this is doing is looking at the unique words within our data. So we pulled 10,000, and we can see that we have over 9,000 of them being unique. So, which makes sense. We're kind of seeing that high quantity of words there, just from the way the data is, sort of built together. Now, what we're going to do next here is kind of do some, and this is kind of in that field again of natural language processing. When we think about this, it's kind of a challenging topic, only because of the fact that we're so used to numeric, like, oh, let's do some visualizations, let's graph this thing, let's get the 5-number summary, let's kind of see those statsy type things. In the field of natural language, it's much more unique in the sense of like you need to look at things differently. So something I typically do here is look at reviews length, so the length of inserts. So let's go ahead and build ourselves a little way of doing that. So I'm going to say length is equal to, we're going to build a list. So I'm going to build a list here called length, and I'm going to say len, so the length argument on I. So this is just a nice little quick lambda here to do this. So length of I for I in data. And then let's go ahead and print here. We'll get our mean length of review. And then we'll also get our standard deviation as well. And then let's go ahead and see this. Should be good. What is it net like? Oh, we gotta round it first. What is it not liking there? Oh, forgot a comma. There we go. Let's see if it works without the round argument, just so you guys can see the decimals as well. There we go. That's what I was looking for. Okay, so what this is giving us here is it is calculating, so for each of these entries or each of these reviews, so it's printing out our mean length, so the average length of the review, so the number of words in there. So it looks like we had about 234-ish, 235 words per review, so notably longer than a tweet. And then the standard deviation is pretty widely variable there. So again, this is something I always suggest is when you're looking at data, comparing your mean or your median, whichever one, again, looking at symmetry of data here, we'll just use average because it's word length, and then the standard deviation. So again, the idea that these are pretty similar, which makes sense if you're thinking about movie reviews. Some people might just, do a few words like, it was good, or something like that. whereas others may really go into depth talking about the plot and the subtext and their favorite actor or actress in there and how they thought that did. So this is a fairly challenging data set in that regard of it's not necessarily all the same length. Something I would suggest is looking at different visualization techniques with text. For the sake of time today, we can't necessarily get into all of them. Although I will say looking at the word length is sometimes interesting. In my work in the psychometrics field, that's something I use when I'm validating tests. I look at the length of words between the two. So if you're thinking about a form A and a form B of a test, if they're meant to be psychometrically equivalent, meaning that they're supposed to be similar enough where like you're not going to see a big difference on there, something that we should think about is looking at test length. So the length of time it takes a user to read a question. So if both questions are meant to determine the same thing, they should be roughly the same length of text. Same thing with total text length of two documents. You want them to be similar, just so that, if someone's taking form A, it doesn't take them, less time just because they're reading it faster as opposed to a form B. So that's something else that NLP or natural language processing kind of factors into. All right, in that case, let's look a little bit at our data. So if I just go ahead and call my data argument here and then print it, we can see this is an array of lists. So you notice these spaces, these ellipses here in the middle. It just means there's a lot of it, but they can't show it all or wouldn't benefit us to see it all. So if I see here, I have the array on the outside with the parentheses, that means it's a NumPy array structure, and then embedded in that is my list. So it's list of lists. So list of a list. So pretty complex data structure. What we're looking at is we can see this is our data set. And then we'll have to pull out where it's the positive or the negative from. So I'll show you how to get to that in a second if you're looking at each item here. And the code it's retrieving at is giving us our dictionary here. So it's mapping the indices back to the original words so that we can kind of see what they are. It replaces every unknown with a hash symbol or like a pound symbol. So I'm seeing if I can find one in here. Of course, apparently on the ones we don't know. So if like, for example, if this was just a pound symbol, that would kind of tell us like it's not there. But what these are mapping back to, if we think about this many unique words, it's mapping each word to that numeric value. So in the list of its frequency. So this first one here, it starts with the most popular word. Also, it does here. Then we can see this would be the 7th most popular word. So it's using the words and referencing a number. So let's go ahead and kind of clean this up a bit to make this a little more readable here. Also, if you guys are curious on how to see, I'm gonna go ahead and just delete this because that's super long and not the easiest thing to read. Let's look at this a little bit easier. So if I want to go ahead and see what it's labeled as in the target data set. So I'm gonna go ahead and just say targets, and then let's go ahead and get the first one. So the first review is a positive review. And again, if we just kind of want to clean that data a little bit so it's a little more manageable, we'll just call that first one. So this is the encoded version of the review. So again, looking at what words there are in there. And then the target is saying like if it was a positive or a negative. So the 1 is a positive. So now let's look at how we can kind of clean this a bit here to make it something we can actually read. All right, so to do this, I'm gonna go ahead and say index, and I'm gonna say IMDb. That's the correct order, right? IMDb, good. And then we're gonna use the function get word index. Oh, I spell it right. There we go. So this function allows you to go ahead and pull these words from this. So instead of just having numeric index references, we can go ahead and get the word. So I'm gonna type out this code, and then we'll talk through what it means. All right, so let me go ahead and share this over. So that's in a shared file now. So this is kind of a cool thing. I'm going to take some time to talk you through this. So what we're doing here, this function up here is getting the word index. So it's saying what word is combined with each of these. So which word goes with the number 1, which word goes with the number 5, so on and so forth for each of these different words. And then reversing, so this is actually a cool way of kind of reversing a dictionary. So like we said, it was set up as a dictionary here, referencing these numbers, so the key value pairs. So pulling it, we're switching the order. So basically what this is doing is it's reversing that index so that I can get the words instead. So instead of having those references there, we're just pulling the different order, the decode it, we called it. So this is the review in numbers. This is the review in actual words. And then kind of seeing this here, for anything that showed up as that pound symbol, these are the pound symbols we can see in here. And what I was doing is anytime is that there was a word with a blank, all it did, by putting this space in here, so there is a white space character, a blank in there, that just kind of puts spacing around the hashes so it still looked like a word as opposed to kind of being like smashed on top of each other there. And you could adjust this for anything you want it. This 0 reference here, so that's just the index reference of this data. So this is the positive review. And if you read through it, you can kind of see why it's indicated as positive. So things we can decode here is the idea of that 1 being the most brilliant thing is the word this. So if you're curious, you can kind of go back and, reverse index those words. So if we wanted to change this, if I want to look at a different review, you can just change that to a 1 or 5, whatever it may be. So if I wanted to look at here and let's see what 5 is, let's see if we can find a negative one real quick. Okay, so 5 is a negative review. So the index of 5 is considered negative. So if I switch all these to 5s, so it's a shorter review too. We can kind of see it here. I've already printed it. Begins better than it ends. So this one was kind of seen as negative. So we can see 5 is an example of a negative. So 1, if we change those 5s to 1s, we see a positive, and if we change them to 5s, we see a negative. All right, so next thing we're gonna be looking at here is data preparation. So we're gonna do what's called vectorizing the reviews. So we're gonna get it to have a bunch of zeros in there, so it has exactly 10,000 numbers. So even if they're shorter, we're gonna fill them up to 10,000 as well. We're gonna do this because that the largest review is gonna kind of, the larger a review is what I'm going to say is it's going to kind of overly weight towards that. So to make these all the same shape, we're going to be dealing with a sequential model again, as we worked with last week. So again, we're going to kind of see the power of the sequential day. Like I said, I believe this was published in 2011. The original study only had about like 80 or 85% accuracy at the end. So we're going to kind of see the power of the sequential model and just how powerful Keras is to see if we can beat that just kind of in our live demo today. So we're gonna make those all the same size, and then we're gonna be doing some transformations to get them into floats, just so that we can actually have this red. So first thing I'm gonna do is type out our definition, then we'll talk through it. I'm going to read through this and make sure I spelled everything correctly here. Okay, all right, that's good. So what this is doing is just what we talked about, kind of making everything the same length. So we're vectorizing it and putting in those zeros as we need to so that they're all that same length of the 10,000 in there. And that was just based on honestly having used this data set before and realizing that that's kind of our maximum, or our longest one was about 10,000 characters there. So we want to make them all the same length. And then the last thing I'm gonna do here is go ahead and vectorize this. So I'm gonna go ahead and say data is equal to vectorize. So I'm gonna call that definition, and then I'm gonna do it on data. And then for our targets, we go ahead and say np.array targets. And we're going to treat those as a type. We'll say float 32. So this is using that vectorizing definition up here on our data. Vectorizing is just one of those processes that when we're going to put something into a sequential model, vectorization makes it just run faster and more smoothly and avoids any kind of the read-in errors that way. Because we can see that if we look at it now, we're getting that binarization of zeros and ones in there. Whereas before it was kind of these lists. So again, similar to how we did it last week, we want to make sure we're inputting those kind of linear looking, the flattened version of the file. So think of vectorization as flattening out a file so that it can be interpreted. And if we look at targets, same concept here. Awesome. Okay, so vectorization, think of it as flattening. Let me see if I can go ahead and get a cool little resource just so you guys have some further reading on that. So if you're looking for further reading on vectorization, my kind of go-to definition here is just think of it as flattening a file. So if we look at what data originally looked like, so if I go back up to here, I got rid of it. It was kind of this like multi-dimensional, like it was an array of lists of lists. So what vectorizing does is we made everything the exact same length. So first off, we've seen we had different inserts of lengths. So by setting a dimension here equal to 10,000, that was our longest entry. So I made them all the length of 10,000 just so that it's the exact same input being taken each time. And then by flattening them into just an array of lists. So originally we had an array of lists of lists. So when we want to input things into a model such as the sequential model, we want array and then just each item being a list in there. So what this does is it kind of like reshaped it. So taking it from a 2-dimensional array just to a 1-dimensional so that it's just a straight list there. So that's the idea of vectorization. It's something that you'll want to kind of play around with a bit. When you're building these models, you'll see that that's kind of an essential step on preparation and cleaning. And then same thing here with our targets now, we see it the same way. So this list here is tagged to this. This one here is tagged to the second. So that's kind of the order in which they're going in there. All right, next, I'm going to be creating some different data sets here. Okay, awesome. So let's go ahead and use a bit of just kind of going back and forth with putting our testing and training in. So what I want you guys to do here is we're just going to be doing some splitting here. So what we're going to do is we're going to split into 2 data sets here. We're going to do the 40,000, so we'll do an 80-20 split. Just for the shorthand purposes here, we can kind of do this manually as well. Since we have our data already set into data in targets, this is another way of kind of doing a manual split of it here. So if we want to go ahead and get that, we can do test. We're getting our testing data. I'm going to go ahead and just say data. And what we're going to do is we're going to go ahead and take everything except the last 10,000. So again, we have 50,000 total. So here's how we're going to do that split. So we're going to take everything up to the last 10,000. Or sorry, I should say up including those. There we go. And then we'll make our Y. And then we want the same thing except the last 10,000. So this is we're just going to reverse those orders here. So if we want to look at these, that's what they're going to look like. So the same shape as we built before. Right. So I'm going to sketch out some notes here for us right now on what we're going to be doing next. So all we've done is we processed our data, we cleaned it, we did some exploration, we've seen different ways to pull it. What I want to do next is kind of that the more understanding part here. I want to make sure we have a good understanding of models. So I apologize for the delay in here, but I want to go ahead and type some of these notes up for us. All right, I'm gonna go ahead and share those over in the code file as well. So one thing too with Jupyter is when you're building these, you can, like I'm just put a new one in here. If you switch to Markdown, it does make it a little more kind of textual. So if you just want to do it that way, that's always kind of a nice shorthand way of making your code readable. So when you're doing Markdown, notice if I click on it, even though it looks like it's on different lines, if I actually want it to be different lines, you have to put enter in between. And then it looks like what you want it to. So that's kind of a cool way of making your notebooks a bit more readable. If it's something I'm just going to read, I kind of tend to do it this way. I don't know why. I guess I just got used to commenting early on. So this is more like this blue text just tells me this like kind of turquoise color, like, hey, this is notes. But again, if you want to kind of get better at it. So I guess the two ways I look at this is if I'm going to present something to somebody. So if I'm building a tutorial, I'll probably do it this way. Or if I'm submitting a report to somebody and I'm going to submit it via Jupyter, I'll probably use Markdown here. You also have these different options of like headers. Those are cool for like titles of different sections. So maybe we wanted to make a header of our data preparation section. But Markdown is kind of the standard of like, I guess you could say if you ever see a tutorial online, they'll probably use Markdown in terms of making it look more professional and readable with your text formatting in there. However, if it's notes that like I'm just using, mine probably looks like this. So kind of the choices of each of those there. So let's go ahead and I can add some more Markdown in here and make it look fancy. So dropout, that's something we're going to see when we're building out these different layers of the models here. So the different ways that we could put it in, you'll see me use that there. So what this dropout piece does here, I'm going to see if I can find a nice article for you that. Let's see. So there's a nice article if you're looking for some more read up on what dropout is. So basically what this does is avoid overfitting. So if you think about, actually that article came with a nice tutorial too. So if you want to do something on the back end and work through some stuff, you can do that there as well. So what that'll let you do, yeah, it's actually a nice little code chunk there. So if you want to steal that later on, not steal, learn from later on, that's another cool little tutorial. So basically what it does is kind of walk you through what dropout is. And overfitting is essentially if you make a model too good on training data, it often performs very poorly on new testing data. So I'm just see if I can find a cool visual about that so we could kind of talk about that. So here's an article on fitting. I'm just gonna kind of show it on my screen real quick and talk you through it. All we really needed was the picture at the top, but I don't want to plagiarize, so I want to go ahead and cite that source. So right here, this is a cool little visual of the idea of fitting versus overfitting. So here, if we're looking at these three different models for mapping to this data. So here, this is an example of they're saying underfit it. So even though the data is split half and half, so half above, half below, which is the linear model here, we can see that that doesn't actually do a very good job of predicting the data. So it's using time and then the predicted value here. So while I might get a few, and again, the idea of regression is essentially you split the data in half. So half above, half below. In this data set, we can see here that it's not really following the trends of this data. So we can see some seasonality if we think back to those time series graphs we've done here in this data. It's really not doing a very good job of predicting, but nonetheless, it's regressed. Here, it's saying this is an example of a good or a robust fit. So the idea of robust means that it accounts for trends in the data. So robust means it's good with variable data or different data that follows different trends. The good fit here, so again, we've gotten half above, half below. We're kind of following that trend to it. The idea of overfitting is that your model is now so complicated that it can account for like every single value. When the idea of you overfit data, it basically means like you've trained your model so well that maybe you have 99.9% accuracy, but it's because you've kind of used that, you didn't increase the dropout rate enough. So in this case, it's overfitted to being this is the most complicated model. So if you look at like, for example, kind of your classic polynomials, linear, quadratic, when you get to higher order polynomials, if your polynomial looks something like this, where it's like, this is probably like what, like a 15th degree polynomial with some extra factors in there. If you have to get that complicated with it, unless you have just massive, massive amounts of data. So when I say that, I'm talking about like you're working for a company like Netflix, Google, Amazon, where like they just have such, when you start carrying data in petabytes, like to where no single computer can handle it kind of thing, you have to start having these giant networks of parallel computers to work with. That's when you see those higher order models. But for the average user, and I'm not even talking about like personal, like in industry, this is kind of where you want to look at, because even some companies, again, when they overfit, it gets so complicated that their model performs very poorly on like new data. So it's like perfect for the data it has, but then it's not good at working with new data. So that's something cool to read up on there. Just nice short read time there on that. All right, so thinking a little bit more here, I'm just going to put in some more notes for us and go ahead and just add on to this one. Uh, Then let me go ahead. I'm actually going to run these, and I'll put this over in our. And if you're looking at the Google Collab file, you're going to see the Markdown version in Collab is just this text feature instead of code. So if you want just text in Collab, you click text as opposed to Markdown. So just kind of seeing the usability between those two. So we're going to use the ReLU function here. Again, we kind of read up on those a bit. ReLU is just a common one you'll see a lot. And we kind of can play around with that and look at some of those other options later on. Dense means they're fully connected, meaning that the layers all work together, so they kind of stack sequentially on top of one another. Some other options in different types of modeling, you don't always necessarily have to have them fully connected, but in this one we want them to be, just because we're using that kind of one-dimensional input data there. So hopefully that makes a little more sense there with the sigmoid there. That's one thing too. And a lot of like when you go to like the online resource style of things, you don't always get the notes that go along with it. So hopefully this is giving you a little better idea of why we're using things like sigmoid and ReLU. So ReLU is just a common one. Again, for sake of time, I don't want to talk you through all the benefits of it, but I would say it's a good place to always start, and you can kind of play around with some different ones on there for the activation. With this, and then sigmoid being the output layer, whenever you're mapping into binary, sigmoid is kind of the default for that one. All right, so let's go ahead here and we can start actually building out our model. Actually, I haven't done this a little bit, so just quick pause here. Any questions on some of those notes we've just taken or the different way that this looks? So if you want to go ahead, if you have any notes or questions you want me to kind of summarize in the chat, please go ahead and ask those questions now. Okay, awesome. So great question here. As you mentioned, sometimes our model may not perform better with new data. So some things to consider here, and then how a data scientist follows up during that time. So I'm gonna go ahead and throw in another note here. So something to think about is when we intake data. So the idea of fitting versus underfitting, overfitting, whatever it may be, that's kind of where the visualization piece comes in, and something to think about how to handle that. So let's take, for example, here, let's say I have 1,000 rows of training data and my data has worked really good on that. So I built a model, I've got good performance, I'm not overfitting, so it doesn't look like that crazy, you know, um, children's drawing of connect the dots. It's a good model, it's got good robustness, and it's good generalization, which means that we kind of see the model going through, but it's not so complicated. So if we're kind of referencing that one I shared over in the notes there, that'd be a good visual of it. Now, what happens a lot of times is things called confounding variables. So one big one in the field of natural language processing is the way that people talk is different from how they create text. So a common problem that I've come across in anything I've worked in natural language processing is the vernacular, or kind of like the dialect being used. So like the formal spoken version of a language versus like the textual language. So acronyms like NP standing for no problem, or the different kind of shorthand we use in text. So WYD, what are you doing? Things like that, especially too when you're thinking about making predictions on things like tweets, only because, for example, like each generation kind of develops their own dialect. So a lot of times, one of the courses I work with is high school students. So their 14 to 18-year-old dialect in terms of like how they may type something is very, very different from how, say, I would type something in an email. So if I'm sending an email to a client, the idea of kind of like the format of which I type those words is probably going to be a little different versus if I'm texting a friend. So the idea of the communication piece there is something that's a common thing you'll see in natural language processing, is where your data is coming from. And the larger it is, the chances there are going to be more errors in there. So what typically happens is when you have this nice prepared training set of data. So let's say that I, scraped all this data from Twitter, and then I went through all of those lines and I manually labeled them, because that's how a lot of this data, these training sets are created, is you're manually labeling. So you're reading through as a human, because that's really the goal of machine learning. So if you want to kind of summarize, AI, machine learning, all these concepts into one, is you're trying to teach a computer how to think like a human. So you're trying to teach a computer how to read something and then decide, okay, is this positive or negative? Would this person buy this product or not? So when it comes down to it, in a perfect world, you'd rely just on a human level of intellect or brain power to do this. However, with the massive quantities of data, it doesn't make sense to have humans reading reviews and making recommendations. If we think about how many users a site like Amazon has, it's just inconvenient. And two, the difference between humans and computers is, computers are more reliable than a human, I guess you could say, in terms of always doing things the same. So if we think about humans, for example, today I have, kind of a runny nose. Like I woke up a little bit not feeling my best. So I'm not at the same performance level as I would be if I woke up feeling 100%. So Whereas a computer is always operating at the same level of, once it learns a pattern, it follows that every time. It has no biases. It has no internal kind of prompts towards anything. It doesn't have a good or a bad day. It's just a computer. So what it does is it kind of looks at that. So the goal is to get the computer to think like a human. So we're training this computer to say, okay, here's 1,000 examples of a positive review. Look for the patterns in there. And the cool part about computers is they can kind of binarize, whereas human brains really don't have that capability to split things into success and failure groups as well. So the idea that we're looking at teaching the computer to look for the patterns that we can't see. One of the most famous examples of this I can think of is a book I read a couple years back. It was of an individual girl who got a piece of mail from Target, and they were using a predictive algorithm to based on shopping trends and sequences, predict if a customer was pregnant. So to kind of see that, if someone is, looking at these 10 different items or 50 different items, whatever it may be, in their online cart, they're likely either considering having a baby or currently pregnant. So let's start sending them stuff to get for the online registry. And this was before the individual had told her parents, her husband, anything. They all started getting mail about hey, for babies, here's what you need. So the idea that you can make those predictions based on trends, that's kind of where computers have that added power to humans. However, again, though, going back to the training data is built by humans because we need someone to go through. So in typical builds of training data, you either rely on user self-identification. So for example, one way I can build training data is, let's say I wanted to work on that introverted versus extroverted personality type. The easiest way to do that would be for me to send out a survey to a bunch of people and say, hey, type a summary. If you had to, in 100 words or less, talk about yourself, go do it. They type up their summary, or maybe I don't put a limit on it and say, hey, look, you can use 1,000 words or 2,000 words, whatever it is. Tell me about yourself. They write this, and then I say, okay, hey, are you an introvert or an extrovert? And they label 0 or 1, I or E, whatever it may be. So they've created my training data by giving me data to work with. So that text input where someone says okay, here's a lot about myself. And then you say, okay, now self-categorize. Are you introverted or extroverted? So that training data can be biased in the sense that someone may not have proper definitions of that data. Maybe they got them reversed. They don't know the difference in the data. So this is kind of the back end of data science that is on the data collection piece, is where that training data comes from is really, really important. So if you're collecting data, you want to make sure your directions are so incredibly explicit. Like I always say, think of talking to a child. If a child can understand your definition of what your data is, that's great. That means that anybody can understand what that definition of your data is. Because if we think about these new projects, oftentimes you are relying upon collecting that data and then having someone self-categorize. Or if you're reading through it yourself, one suggestion would be, if you have 100 pieces of data that you're using for training, is not only you read through it and categorize, but then have somebody else do it. And don't tell them your answers. Have them do it. Have 5 more people do it. Have 10, 20 more people do it. And then use the data that had common things. So if everybody said, review number 1 in this data set was positive, cool, I'm definitely going to use that as a positive example. But if for the second example, we were split, half the people thought it was negative, half it's positive, that's probably not something I would want to use for a training model. So you want to have that idea of consensus in your training data. Whenever you have humans creating training data, is you want more than one set of eyes on it. You want a team of people looking at it who all understand what the data is that you're looking at. And then how the data scientist kind of fixes these things. Honestly, there's no one size fits all answer for that. You'll see a lot of marketing options where it's new platforms are you don't need a data scientist. Teach anyone to use this platform in 10 seconds, and then they can create advanced machine learning models. I've seen that as a new trend in industry. And again, no hate on the people that are making these programs. They're really cool. And for someone who understands what the output is, it's really useful. It kind of shorthands a lot of the Python coding or the work in R that you might see. However, that's kind of where the gray area of having someone who really understands, or a subject matter expert in the field in the data science, is that you understand those trends of, the machine might give you an output, but that doesn't mean it's great. You're understanding that you should be looking at your training data. I don't care how large training data is. I always kind of read it and spot check it. If it's 10,000 rows, I'll probably read every 50th or 100th row just to kind of be okay, let's see what this data looks like. Let's see what's coming in. Is there any errors I'm spotting? I'm looking for null values in data. So the idea of when you create a model, you then want to go back and kind of review every single phase of it and think of where those confounding variables can occur. And a confounding variable just means like something you didn't account for or something unexpected that happened. So that's kind of where the, you know, every time you do one of these projects like this, even though like now, like I'm telling you, like, okay, this data is pre-built, like it's going to work pretty darn good, because it's an already clean data set. If this were, as I would call, in the wild or like real world data, the first thing I'd be doing is looking at, I would read a bunch of these reviews, and kind of categorize them myself, see if I agreed with the ratings on them as well. All right, let's go ahead here and start building out this model. So we're gonna go ahead and define our model. So I'm gonna kind of do this one block by block. So let's go ahead and just call it model. I'm gonna use TF dot to reference our TensorFlow. I'm gonna say Keras, and then we're gonna use our sequential model. And we'll do a little bit of reading at the end here to talk about some of those other model options. Sequential, honestly, though, is kind of like the industry standard. So pull up that resource real quick, and we'll talk at the end about the different modeling options. Next one we're gonna do is build our input layer. So we have our model, which think of as like a blank canvas, and now we need to sketch out the design of how the data is gonna get brought in. So here we're gonna say model.add, and then we're gonna call our layers. We're gonna use dense because again, we said these are all connected. Here's one way to put the dropout. So you can either do the dropout as a whole number like this, so 0 to 100, or you could just list it as decimals. So I'm just gonna kind of do it interchangeably throughout this so you can kind of see. And then for our activation, so what's recognizing that, like I said earlier, we're gonna use that ReLU or ReLU. Honestly, don't know the formal pronunciation of that word. And then for our input shape, here we have that 10,000 and then blank after it. So we're having those 10,000 individual things shoot into it. Oh, what is it? I spelled that wrong, didn't I? Active. What did I spell wrong? Oh, I have a minus symbol instead of an equal. There we go. What is it not like now? Oh, I need a space here. What is that not liking? All right, let me just code check this real quick. There we go. Okay, I had one. There it was. I had something spelled wrong in there. So I'm gonna go ahead and share that over. Awesome. Thank you for the catch right there. Not having the equal sign there. Perfect. Okay. So that's building our input layer. So it's saying it's coming in of that 10,000. So if we think about that shaping, that common term up here, so it doesn't have anything with it because it's just kind of reading these as individual inputs. So there's no input output. So it's just one data point coming in with 10,000 pieces of that data. All right, I'm gonna go ahead and type these out and then explain them. So we're gonna put a couple different hidden layers in here. So what that means is just a different shape. And again, these are the defaults here of the noise shape. Sometimes you have noise shape. That's something, again, I'll try to find some further reading for you guys on, but we don't have necessarily the time to discuss it today. But for our more simple model here, none is the default, same with seed being none. Let's put another one. So the kind of way we're numbering these layers is 1, 2, and 3. So the dropout and then the dense arguments are tagged. So they kind of go hand in hand. So it's like it's technically they could be thought of as one layer whenever we see a dropout dense combo here. But for the sake of like the visual piece to it, kind of looking at them individually seems to help. That's the way I've always kind of thought about it. Let's see, 0.2 and our last one. And you can put those all in one block of code. I just kind of want to space it out so you guys get a little more of a view of kind of each piece going in there. And last thing, once you've got that set up, you can go ahead and check out your summary. So by calling model.summary, this gives us some information on it here. So we're dealing with our sequential model, then showing us the different pieces to it here. I'm trying to find something, a quick read up for you guys to kind of talk a little bit more about understanding this model output. Here's another good resource for that. Again, for just sake of time, I don't want to read through all of this together, but if you're looking for further reading, there's another cool piece of kind of reading through like what each of these means. So the parameters is kind of an important argument. Again, for the sake of time, I'd suggest reading up on that article I just shared. It deals with like the biases in there and kind of the weights with it to see how many of those parameters we have. And then this just makes sure that your parameters are of the right shape so that they're all trainable. So again, my apologies. You see, I kind of alternate between just commenting out things. So one thing you'll notice is I kind of do this, depending on what the standard zoom is you work on your screen. Like if I zoom out more, I can kind of see more with this. However, the cells are kind of always shaped the same way. So there's like a set amount of words you can get on like one line here. I don't like typing comments. Like if I just keep doing this, like if you're commenting your code, this is really bad practice, just because it makes it super hard to read. You'll notice sometimes if you go on sites like Stack Overflow, when people are commenting things out, they're just like typing away, and then it's like this super long, ugly cell. So one thing I would advise is if you're using this shorthand way, mostly because I find it inconvenient to go up here and click Markdown. And I like how it kind of pops out with this turquoise color for me. If you're looking at the Google Colab, it's like a bright green for the notes. So I always just kind of keep any notes in this way. Again, if you prefer Markdown, like I said, if this was presentable to a client, I'd probably use Markdown because it looks better. But for my own notes, I kind of like doing it this way. So this is kind of just talking through the specifics of what we're going to do next. So when you see the idea of compiling a model, what it just means is like you're setting up the specifics of the training parameters of like how the training should occur. So we use the Atom optimizer just like we have before. Again, I shared a resource, I believe it was last weekend, on the different optimizing options. Atom's pretty common. It has some cool self-adjustment there for the weights and biases during the training. So it tries different options and it self-regulates on those. Binary cross entropy is the fact that we're using binary. So that's the loss function here. So we're looking at, since we're doing a binary output, that's why that one's going to kind of be the default there. And then accuracy is going to be for our metrics that we'll use to evaluate this. So it's looking at accuracy as saying it's either improving or getting worse kind of thing. Whenever you do classification, that one's pretty self-standard there. So let's go ahead and get our compiling. Let's type it this way. One of the more annoying ones to make sure you're spelling right. Go ahead and run this before I talk through. All right, cool. Sometimes so you'll see that there's different ways to like type these out. So maybe you want to do it like this way. This is a pretty common one when you hit enter after the commas. So and it runs the same way. It's just a readability preference. The more complex some of these things are, it helps to kind of go line by line. That's why and a lot of times in documentation, you'll see that where it's like it's shown line by line. It doesn't make a difference. Like I shared it over in the shared files just as a one-liner kind of thing. Here it's still reading the same way. It's just kind of a little more presentable, I guess you could say. And then while you guys are getting this down, I'm gonna go ahead and type up some notes here for you on a little more understanding of the epochs and of the batch size argument. Let's put that over in the shared file. So when we do our results here, so we actually fit our model, we're gonna see a couple of things here. So the batch size refers to the kind of chunks that we're taking of our training data and putting it through the model each time. so how large they are. So the idea of propagation through this neural network we've built. Kind of a rule of thumb here, a larger batch size makes your training go faster, but it may not converge as quickly. So convergence is like reaching its end goal. So kind of saying like, okay, like I guess you could say the model completing its learning segment. That's the idea of convergence there. Um, Smaller batch sizes means it's going to train a little slower because to get the data, it's going to be taking it in chunks. So it's processing the data in like chunks of data. So chunk of data goes in, chunk of data goes in, and it's continuously updating the model that way. So it's a kind of rule of thumb, you want to be on the smaller side with your batch sizes, just because it might take a little longer to train the model, but it's one of those things where you usually get a better result the smaller the batch is. And then epochs, we've talked about those. So here's kind of our working definitions. They're the number of iterations over the entire training data set. So it's the number of times this whole batching and processing occurs. And this is where we can kind of see a good way of determining if we've over or underfit our model is by playing around with the number of epochs here. So we'll kind of see there like, okay, if we see this, the idea that we kind of set these epochs to different amounts to see how well we're fitting, and we're going to do that by comparing accuracy, so which is the actual classification, and then the validation accuracy, so like when it works with that new testing data. And then something else to think about here, we'll include this over here. So default batch size, depending on who's the person telling you it, they might always give you a different number here. I recommend between 30 and 40 and just kind of scaling up, by different chunks of time there. So we'll kind of see the different results here. So what we're gonna do is we're gonna play around a lot here with our model. So this is gonna kind of involve that idea of like that question we had earlier, what do we do when it doesn't work the way we wanted it to? So let me go ahead and type this out. I forgot if I used capitals or not. Sorry, I'm just going back to see if I used, I used capital letters. So capital X, lowercase y. Okay, so I left some blanks in here, and this is where we're gonna kind of play around a bit. So the two things we're gonna mess around with here are the epochs and the batch size. And then let me go ahead and put in our next line here, just how we're gonna do our evaluation here. So we go ahead and say print. So these are gonna be the last two lines of code we need, and we're just gonna kind of play with these for the remainder here to kind of talk about that process of like, okay, how do I actually know if this is good? Let's talk through what we have here. So this is our results. This is where we're actually doing our fitting. And what we're gonna see here, the default verbose here is gonna kind of be set to that 1, so we can kind of see some output, but not too much. So we're inputting our training data, so train X, train Y. Epochs, I have blank right now, same with batch size. And then our validation data. So this is the idea of the accuracy versus the validation accuracy. So this is where the idea of fitting versus overfitting comes into play, and we're going to kind of examine that in two ways. Actually, let me put one more line of code in here, and then I'll share that over. Okay, so the two things we're looking at here is what these outputs mean, and this is one of those kind of key parts of the why the human element to data science is important. It's what comes out of here. So there's two different measures we can get out of here. We can get the accuracy of our training, and we can get the validation accuracy, which is actually working with the testing data. So understanding which is which is kind of key. The easiest way is that this starts with VAL and this starts with VAL. So it's kind of where that's coming from. So accuracy refers to your model, and then the validation accuracy refers to how did that model do at the end. So let's just start off with something simple here. Let's just do epochs of being 1, and we'll say batch size. Let's start it off at just 30. So I'm going to go ahead and run that. Oh, where's it saying? Oh, my Y should be lowercase. Sorry about that. So when I'm running this one may take a little bit. You're just seeing how it's going through. So this is my epoch. And you're seeing is it's processing through these chunks of data. So if I look at that size of the data into chunks of 30, that's how long it took. So smaller batch size, slower training, right? And let's go ahead and see now if I look at accuracy. Let's see, it's not liking how I'm calling that. Why is it not liking that? Is it like this one? What does it not like here? I have one too many parentheses at the end. Let me go ahead and fix this really quick. Why does it not like that? Shouldn't have 3, I should just have 2. Okay, I see the problem. These are too many here. Sorry about that. For the history argument, we don't want that there. So that should fix this. And I'll update the code in a second. There we go. So let me go ahead and update that in the shared file there. I forget, this is more like calling off of a column on a data frame as opposed to anything else. So there we go. All right. So now let's talk through this. We had 1 epochs, and then we had a batch size of 30. So that smaller batch size, it took it a little longer to execute through just because it's chunking it. So it's putting the data in smaller chunks. So here in our output, I mean, not that this took terribly long, but still longer than you might think. So here's our loss measure, and here's our accuracy of that, and then our evaluation loss, and then the evaluation accuracy. So we're kind of comparing these two here. We see we had an accuracy with the data. So when we're looking at our training data, there was our accuracy there, and then here was our validation accuracy. So even with just 1 epoch, we actually beat the result. I can't think of what it was, honestly, off the top of my head, but I'm pretty sure, like I said, in that Stanford paper, 9-ish years ago or so, they were only in like the low 80s. So now we want to kind of play with these different epochs and batch size. So let's see if we just change the batch size to like 100. Let's see what that does for us. So if we're looking here, comparing how fast it's running, it took us 13 seconds before. Now it took us only 6 seconds. So batch size highly depends on how fast it trains. And now if I kind of look at these results, we can see that by using a larger batch size, we had a higher accuracy and an even higher value accuracy. So playing with that batch size there kind of determines, okay, like how quickly are we learning? How good is the convergence? So far it's looking like the idea of increasing my batch size is pretty beneficial. I'm seeing that both of these measures went up, both the training as well as the validation. All right, let's try if we change our epochs here. So from 1 to 2. So you see it's going through the data once, and then it's going through the data again. So it's taken about 6 seconds for each time. So I had 0.933, now I'm at 0.96, I had 0.89, now I'm at 0.88. So things to consider here. This is the idea that we're actually seeing some overfitting occur. So as I increased my epochs, my validation accuracy went down. So it was at 0.89. Now, again, it's marginally, but it's still decreasing. So this is the idea of where we're starting to see overfitting occur. So if I increase those epochs again, let's say I make them 5. So again, we're seeing the time here. So the more epochs, the more iterations through all the data. So we're seeing our accuracy here is increasing, right? So the more times I'm iterating through, the more accurate my model is. So the better predictor I'm getting here. In that classification, we're seeing an increase again. You'll notice the increases here happen to be more marginal each time you go through. But if I'm looking here, this is also increasing. So the more that my accuracy increases, my value loss is also increasing. So if I go ahead and rerun these now, we're at 0.96, we're at 0.97. Let's see about my validation accuracy. So I was at 0.88, about the same. So from 2 to 5 epochs, I'm not really seeing much of a difference in terms of validation accuracy, but I am seeing an increase here in my fitting of the model. So think of this first one here as you can examine how well it fits. So the idea of fitting comes from looking at accuracy, and then overfitting comes from looking at that val accuracy. And for another demo, let's go ahead and try something a little different here. So let's go ahead and try just 2 epochs and then maybe like 400 for a batch size. So again, this is part of the data sciences steps to this is kind of going through these, and you want to try to optimize your model. So here I'm seeing now that my accuracy so far, the best was I was at that 0.97, and it looks like this is going to be a bit better. So let's see. So now I'm over 98% accurate. So in my training, and then let's see how this works. I'm at 0.88. All right, and it stayed about the same. So rule of thumb is if you're looking at val accuracy, like you notice I'm kind of looking at these first 3 to 4 numbers here. That's real. I mean, don't get me wrong, like the 18th decimal place is probably pretty cool if you're performing a white paper type thing. But for like real world stuff, like 3 to 4 decimals is probably all you really care to look at. So it looks like increasing my batch size actually helped things out a bit there because now my program's running faster and I'm kind of seeing these things remain stagnant at a higher accuracy on my training. So let's try doing something here. Okay, so let's say I made my batch size like 500 and then I made my epochs like 10. This one might take a moment to run, but let's go ahead and try it. So with that large batch size, you're noticing these are running really quickly. It's only about 4 seconds per epoch. So I'm watching my loss. I'm looking at my accuracy. And then we're seeing that val loss increase though. So again, as this accuracy goes up, typically your val loss also goes up. Then we're noticing here a drop off at these later epochs in terms of my value accuracy. So let's go ahead and see how that worked out. So I'm at over 99% accuracy and I'm still above 88%. So it seems like what's affecting us more here, as opposed to the epochs, is it's the batch size argument. So for this one, we're getting that convergence as we increased our batch size. So the bigger our batch size is getting, it seems to be giving us better results there in our val accuracy as well as, our validation accuracy here, as well as in our accuracy. So this is something to play around with in terms of the idea of fitting, is how well it fits. And then again, if this gets lower, so if these kind of work inversely, as you see that accuracy increasing, if your value accuracy is decreasing, your validation accuracy, that's a good sign of overfitting there. So as long as these are pretty, if this one stays constant as you increase your epochs and your batch sizes, that's a good sign. If we look at doing these 10 epochs, maybe let's do it with something lower. Let's just try 50. This one might take about a minute or two to run. But again, this is part of the learning process too, is learning to read these outputs and experimenting with these things. About 10 seconds on this one, right? Yeah, 10 seconds. So this one will take about another minute or so to execute. So if we look at the results we had here, so we had 0.99 and then 0.884. Let's see how this works out. So we can see the build up here in our accuracy coming. We've seen a drop here, but then a good increase on that third epoch. So it learned something there. And we see our validation accuracy was constant for 2, and it's starting to increase again. Then we see a little drop off there as those epochs continue. So this is the experimentation phase here of playing around with different ones. So this is something I would be documenting. Like you see personally, like right now, I'm just rerunning these same code blocks just for demonstration purposes. This is something you'd want to actually kind of like separate into separate lines of code, or just keep like notes somewhere on your results. So if I run these now, we had 0.99 down to 0.98, still pretty good. Let's see how our validation looks here. So 0.884. 0.880. So this was actually worse than our last one here. So we could kind of see this set of data is more reliant upon the batch size we're bringing in as opposed to the epochs necessarily. So I think our optimal one here was, what did we have? 502. I think that was our go-to so far, was our best one yet. So let's rerun that one again to kind of see where we were at there. Let's see, 0.99, 0.8, ooh, 879. Maybe we want to change that to 3. I forgot which we had our optimal one there. It was 5. Let's try that. That might have been our one that gave us the best results so far. Yep, okay, accuracy is looking really good. Val loss, okay, let's see where we're at. So still in 0.9s, 0.8s, awesome. So pretty good stuff. Again, this is one of those processes where it just comes with repetition, building through, trying out different scenarios. There is some more kind of like advanced ways, like you could write, programs to test out a bunch of different epochs. So kind of similarly how we did that cross-validation piece, there is ways to do that. However, they're really confusing if you haven't read through them before. So I want to kind of keep it simple and just work with the usability of a notebook here, just kind of alternating these yourself. So again, in practice, if you don't want to write a really complicated loop to optimize these, just control A, C, V, copy this stuff, maybe rename your models. So like up here, you can put this all in one code block, call them model 1, model 2, model 3, model 4. There's some other experimentation you could do with swapping out ReLU for the other activations. So I kind of want to end today with just talking about a few things in the documentation. So the first thing to read up on is some of these different models options. And then here's sharing over those different activators. So if we're looking here, the different models. So again, we've worked with these sequentials so far. So this is kind of like our go-to, like I said, like not totally standard, but like the standard. And then there's some different ones here. So the sequential model, listing out your layers, single input, single output. So the idea here, this is the one we've worked with so far, where we're inputting something that's one-dimensional and it's coming out with a one-dimensional output in that classification. Functional API. So this is something you can look into. So this is the kind of large level model, but again, for the demonstration purposes, we kind of stick with the sequential. So for these two here, functional API, if I go ahead and just click on that, this is a good demo here to work through of your functional API. And if you want to view the kind of source code, if you click view in collab, it'll give you a similar file to the one that I share in terms of like what you can look at here. So this is a cool little tutorial you can look through if you want to learn a little more about that. That I'll kind of walk you through what the functional API is there. It's a lot more, I guess you could say, it's a little different, the coding of it. So again, the code is usable here, especially if you're looking at the collab file. But personally, I prefer the sequential because most things you're modeling, you can kind of boil it down to the success failure type level, and it gives you more understanding with that. Model subclassing, this is the most kind of advanced one. So their demo here is okay for it. However, this is one of those, it's a very, very high level thing. So if you're still at the point of where you're being introduced to these concepts and you're trying to get good at it, my advice, kind of like we've stuck with so far, is getting really good with sequential models. So we worked with image classification last weekend. The focus of our weekend, this one, is text classification. So we'll be doing more with that tomorrow in the sentiment analysis piece. But again, this is kind of that expanded learning if you want to go a bit farther. The other thing to kind of get good with playing around with here is going to be these layer activation functions. So if we think about this is kind of what it's looking for to work with loss. So you can see here, ReLU is kind of the first one they talk about. So the rectified linear unit activation. Cool interview question is, what does ReLU stand for? I've had that actually from a client. They're asking me, I showed them some demo code and they asked me what that was, and they were actually impressed. I knew the definition offhand. Going through, so again, kind of talks about the advantages of Sigmoid. So you see we use this one, those two common ones as well. So the idea of like, okay, like if it's 0, 1, like that binarizing, putting my values between 0 and 1 makes sense for Sigmoid classification. Softmax is another one you'll see on like a lot of demos and tutorials. They use that as well. Soft plus, not as common. I'd say same with soft sign, and then kind of these less common ones. I'd say the most 3 common ones you'll see are going to be ReLU, Sigmoid, and then Softmax.